As some of you might know, I help Christine organize these events. A few weeks ago, Christine came up with the idea of doing a session focused on RAG. She only had one speaker lined up at the time, so I offered to do a short introductory talk. Most AI enthusiasts have heard the term RAG, but not all know where it fits on the AI landscape. My goal today is to set the stage for Dimitar's upcoming deeper dive in the second session. I want to give you a high-level overview of the problem space RAG addresses. Before we dive into the core of today's talk, I'd like to say a few words about myself and my journey with AI. Back while I was working at ETH after my master's degree, I first encountered the concept of artificial neural networks. The idea itself wasn't new, but back then, PCs and workstations were finally powerful enough for people to experiment with artificial neural networks. And I was one of those people. On the right side, you can see the back cover of a book on neural networks that I bought in 1990. To give you some context, Amazon didn't exist yet and Germany was still using the Deutsche Mark. This was about a decade before the transition to the euro. What's fascinating is that the fundamental building blocks, like artificial neurons, weights, activation functions, multi-layer perceptrons, and the backpropagation algorithm for training, all existed back then. And those exact same concepts still form the foundation of today's cutting-edge large language models. But even an older LLM like GPT-3 is about 50 million times larger than the models I was using at that time. But now, let's jump straight into our main topic. Let's talk about what I call the AI data gap. On the left side, we have the data the LLM was trained on. This includes enormous amounts of publicly available data, everything from websites, source code, and books to magazines and newspapers. When we want to integrate AI into our business processes, this data is insufficient, though. We also need customer lists, transaction histories, sales reports, internal product specifications, and daily communication data like emails or chats. The public data used to train these models completely lacks this information, which is most crucial to your business. Furthermore, the intrinsic knowledge of the LLM is always outdated, so all events and latest information after the so-called knowledge cutoff date are missing. For GPT-5 Mini, this knowledge cutoff date is May 31st, 2024. This is the AI data gap. So how do we fix this? How can we make sure that our LLM knows our internal company information and our most current data? Can't we just retrain the model using all the data we want it to know? In reality, that is almost never an option. And there are three major reasons why. First, many of today's leading frontier models are completely proprietary. You simply don't have access to the raw weights, so retraining them isn't even supported by the vendors. Second, full training is very expensive. It requires highly specialized hardware, and the data preparation and compute time can take months. Third, full training requires highly specialized data science expertise. If you don't do it perfectly, you run into a massive technical risk. The training process can accidentally overwrite the model's existing capabilities. In AI, this is what we call catastrophic forgetting. You could spend millions of dollars on training only to end up with a degraded model that has lost its core capabilities. So full retraining is off the table for most businesses. What other options do we have? What are the possible ways to influence how a model works and what it knows? There are really only three ways we can influence how an LLM works, and they are laid out right here on these three clipboards. Let's break down what we can achieve with each method. First, on the left, we have hyperparameters. These parameters influence the inner mechanics of the LLM and are specified with every single request you send. For example, hyperparameters like temperature or top P define how creative your model is. Others define the response format, for example, requesting a JSON output. But there is absolutely no way to add new information using hyperparameters. Second, fine-tuning. Think of fine-tuning as a lighter form of training. We only adapt a tiny fraction of the model while freezing the rest of the neural network. But this still requires quite some time and money. As the slide says, fine-tuning is all about form over facts. For example, you can fine-tune a model to speak like a lawyer, but you cannot use it to inject factual data about your latest legal case. So we only have our third option left, the context window. Most of you have heard this term already. The context window is the entire space of input data we send to the LLM at the moment of the request. All we want to send to the LLM needs to be placed in the context window. The context window is the only way to inject current factual information into an LLM. If we look at the diagram on the left, it acts as a funnel for everything we send to the large language model. This includes the initial user prompt, system prompts, background instructions, and any actual document content or retrieved knowledge we want the AI to look at. On the right, we can see exactly what roles this context window plays for our application. Proprietary and real-time data. This is where we feed in the live business data the model wasn't trained on. Short-term memory. It allows the application to remember past user requests and previous model answers, keeping the conversation continuous. Instructions and framing. It defines how the model should behave and the boundaries it needs to follow. Thinking space. For modern reasoning models, this is also where the results of previous reasoning steps are held, so the model can process complex logic before generating a final answer. The context window is our primary tool for giving the model the right facts, but we need to make sure we are feeding it the correct information at the right time. Feeding the right information into the context windows is not a simple task. This brings us to what I call the data dilemma. The capacity of the context windows is small compared to the amount of company data. On the left, we look at context window capacity. From GPT-4's 32,000 tokens to newer models, there was a massive leap. The newest models support hundreds of thousands or even 1 million tokens. This is still small compared to the company's entire data volume. Even a small company easily generates 1 to 5 terabytes of data. A medium or large enterprise is sitting on tens or hundreds of terabytes and sometimes petabytes of files, emails, and database records. In many cases, less than 1% of your corporate data would fit into a context window at one time. On top of that capacity constraint, we have a data quality issue. Some information in that massive corporate pile is outdated, some is low quality, and some is flat out redundant. So in reality, the core engineering challenge comes down to this big question mark in the middle of the slide. How do we dynamically select the most relevant, reliable, and current information from our huge enterprise pile? We need to find the exact needle in the haystack, and we need to find it fast, and this is precisely where RAG lives. The central principle of RAG is simple. Extract the most relevant, up-to-date proprietary data to provide the LLM with the exact context it needs to respond. This architecture relies on 3 distinct steps that spell out the acronym itself, RAG. First, retrieve. The system automatically searches your company's data and retrieves the most relevant pieces of information based directly on the user's initial prompt. Second, augment. We take that freshly retrieved data and pack it alongside the original prompt and system instructions into the context window. So, we are augmenting the prompt with company data. Third, generate. Finally, we pass this fully enriched context window down to the LLM. The model reads the data provided and generates an accurate, grounded response based on the facts we handed it. In this way, RAG can bridge the AI data gap. Let's look at this same concept using the diagram. This maps out the actual data flow of a RAG system. First, retrieval. When a user prompt comes in, it triggers an external, highly specialized search engine. This search engine filters through your company data and extracts only the most relevant content. Next, augmentation. Here, the user's prompt is combined with that freshly retrieved relevant data and the other data that goes into the context windows. Finally, generation. This enriched context window is fed into the LLM, which then generates the grounded response you see on the far right. In this entire architecture, the trickiest part by far is the retrieval phase. Finding the absolute best data among terabytes or petabytes of unstructured enterprise data and finding it fast is quite an engineering challenge. By best, we mean data that is relevant, current, accurate, and contextually important. We will hear more about this challenge in the second session. Let's wrap things up. Here are the key takeaways from this introduction. First, LLMs do not inherently understand your business context or proprietary data. Second, the only way to teach an LLM your company-specific data is to provide it directly in the context window. Third, the core challenge is selecting and delivering the most relevant information to the model and doing so as fast as possible. And finally, Retrieval-Augmented Generation, RAG, is a fundamental approach to achieve this. This brings us to our next session. Thank you very much for your time. After answering some questions, I will hand over the floor to Dimitar for the deeper dive into RAG.